So, hi guys, thank you for coming here. My name is Pavel Hardak. I'm a product manager with Workday Analytics.
And I'm Jianneng, and a software engineer.
So this session, we will speak about the lessons we learned when we use Apache Spark for the self-service data prep a little more in our SaaS world. So as a public company, we have this statement, which means like if you make financial decisions based on our presentation, you cannot blame us. We do work to make Workday stock more available. So what we're going to cover today, short introduction about Workday as a company, our platform, what we call Power One, and then of course Prism Analytics. And since we're here, like you probably understand, it's powered mostly by Apache Spark. And most of the time we will speak about the production and the lessons we learned. And then maybe we'll have like several minutes for questions later. About Workday. So some people call Workday the biggest SaaS company you never heard of. And the reason is like it actually like caters to HCM and financial markets, not to traditional like data scientist or engineering. So started about 13 years ago with the single HCM and then finance product. And now we have like more than 20 products in the SaaS world. 2,500 and more customers, including 40% of Fortune 500. And last year revenue was $2.82 billion, 30-year increase year to year, so growing fast. So when you speak about HCM product, you usually have people who either don't like or really don't like the software, not in Workday. In Workday, each year we run satisfaction survey, and we target 95% satisfaction. Year after year, we beat it. Last year, it was 98%. And you see like it goes across the board from young companies like Netflix and to the very old companies like Bank of America. So people really like Workday. So what is the secret? Of course, there are many, but one of them is about technology. It's about the platform. Unlike many other solutions, in Workday, we run on the one suite, which is like one platform, where we have the platform, the technology, the security, all of that in the one platform. So all applications share the same infrastructure. One piece of that is object data model. So some people will call it memory-centric graph database with object-oriented features. So it's great for transactional payloads, and all our applications use it. But it's not exactly the best fit for the analytical payloads and where the Apache Spark comes in. Security is paramount for us because people trust us with the most private data, both in human resources and finances. So of course we use everything is encrypted and everything has audit, in addition to multiple layers of security on top of that. And reporting and analytics. So the thing is like, of course, once you accumulate a lot of data in your applications, you can say like, I can take it out to external data warehouse and analyze it there. But once the amount of data gets big, you say it actually makes more sense to have in-app analytics. So I have it secure, I have my data which is like really fresh, up to date, and also I uses the same security and the same user interface and patterns as other applications. So in Workday, we do like the full cycle, execute, analyze, and plan. In this presentation, we will focus on the Prism Analytics, which is the main product in the analytics place. So Prism Analytics does everything you expect from the full-grown analytics application. You can bring third-party data. You can get data management, preparation, data discovery using several different UIs, data discovery like dashboards, scorecards, reporting, etc. Why Prism? And the reason is like it's about data gravity. Once you accumulate a lot of data inside your platform, it actually makes sense, instead of like taking this data out, to bring more data to you so you can get like more insights by combining the HCM, financial, recruiting, expenses, and other data with external data and analyze it from different angles. So this is what we call Prism. How it works. First, of course, data acquisition. Data from Workday, HCM, or finance, which is pre-integrated, so it's easy to map. but also the data from other system, operational system, like CRM, like Salesforce, service ticketing, like ServiceNow, legacy systems, people who switch to Workday, but they still want the continuity from the previous years, some other industry systems, like total compensation. You have a base and your bonus in Workday, but your stock allocation in other systems, so you want to bring this in to get the better picture. So you ingest all this data, and that's where data preparation comes in. You need to clean your data, transform, blend with the Workday data, then apply security permission, and then publish. So it's like one, bring the data, then prepare the data, publish the data, and then analyze the data using one of the tools or any of the tools in Workday, worksheets, reporting, data discovery. How it actually maps to the technology world. So if you take all big Workday architecture and Workday architecture and put it into kind of zoom out of it, so it's a top left corner. And we say, like, let's look only on the Prism. So in Prism, we have a Prism application server, which runs as a Dockerized application. And it connects to the Workday Vault. But that's a pretty smart guy. And one of the smartest, it actually doesn't do much of heavy work. It outsources it, actually delegates to the Hadoop cluster, where we run like 2 long-lived applications, interactive data prep and query engine, and one on-demand data prep publishing. So HDFS keeps the data for multiple customers, data prep, data publishing, and query engine. So, and in this talk, we will focus on data prep, first 2 engines.
Okay, thank you, Pavel, for the introduction. So now we've seen the bigger picture, we can finally dig into what data prep is. So you'll notice that there are 2 components of data prep. There is the interactive part, and there is the publish part. So what is the difference? Interactive is where users build their pipelines interactively using our UI. And as they build their pipelines, they can see results interactively in real time. Whereas after they're done with their pipeline building, they can publish it so that downstream reports can utilize it to get accurate results. So let's dive a little deeper into, say, interactive data prep. So this is an UI that the user would possibly see. So you see on the left side, we have transforms that users are able to add, such as join, union, filter. And on the right side, you're able to choose the number of samples to sample from. And then finally, you get examples and statistics based on the number of samples and also based on the pipelines you have. And of course, this is a UI product, so you click on edit, and you're able to edit your transforms visually, interactively. And again, as you build and change your pipeline, you see results. And this result is being powered by Spark. So then this is interactive. Then for publish, after you're done, you click the publish button, and of course, this is also powered by Spark, as we saw in the previous architecture diagram. So then, what is the difference between interactive and publish? Well, there are quite a few. So first of all, you see that for data prep, for the interactive data prep, the data size is smaller, right? Users expect real time, so the sizes of data you sample cannot be too big. Otherwise, the processing power will not be fast enough. Whereas for publishing, it'll be a lot more. Sampling, of course, right? If you have less data, then you need to be more careful about the data you sample. Otherwise, if you have many joins or many unions, it's very easy to not have any results out in the end. Then for caching, interactive requires caching because users, when they make edits, all these changes will be made on an incremental basis. So users would add an extra stage or add an extra column, and you want to be able to reuse previous results so you can return your result as fast as possible. Whereas for publishing, everything is done in one shot, so caching is not necessarily the focus there. Then for latency, again, the interactive is a interactive iterative process, so it's expected to be fast. Whereas for publishing, we really just care about the performance being very consistent, because a lot of times publishing is being done on a schedule. So if publishing is done every hour, then you cannot have some publish go under an hour and some publish go over an hour. Okay, so if you haven't noticed, you see that this is the same plan, right? You have all these different characteristics and different requirements, but ultimately what's being executed is the same. And this is one of the main reasons we really value Spark as an engine, because it's suitable for both interactive and batch cases. The only difference really there is, again, the data you feed into it and what you do with the result. Okay, so the fact that we can use the same plan is a big plus for us. So then what other reasons are we using Spark? So let's dive into the Prism logical model. So like a SQL system, Prism also has a set of logical operators, but because there are domain-specific use cases that Prism supports, we have a superset of them. And the interface between our logical plan to the Spark logical plan then is through Spark SQL. So Spark SQL can either be done through printing SQL statements or directly using the data frame dataset API. And because we also have custom plans and operators, we also implement custom rules and strategies so that Catalyst can optimize it and also translate it to physical plans. So to give an example, right, we have data prep interactive that we just talked about. And the part of it is sampling. So the part it would work in the Prism side is we would have an ingest sampler that we compile into our logical plan. And then during compile time, it would be compiled into a Spark plan by an operator that we have created called logical ingest sampler. And through a Catalyst strategy, it would then be translated into a physical plan, and finally, the RDD. So the benefit here is Spark allows us to be able to extend their logical plan to suit our needs. So the extensibility of Spark is also very important to us using Spark. Another aspect that to show Prism is Prism is able to use the extensibility part of Spark, the data types. Prism, again, we have HCM use cases and finance use cases. So our type system is naturally richer than what Spark offers. But Spark has the struct type and struct field classes that we can use to implement these additional data types. To give an example again, Prism has a financial use case, right? So one of the primitives in finance is a currency. What is a currency? It is an amount and also a currency code. So in this case, we're able to use these two primitive constructs to create a structure type called currency, and that can represent this information. And at compile time, we're able to generate these schemas, and then we ship it to Spark, and Spark is able to handle the execution because we can also modify that part as well to handle how two different currencies are being aggregated and also being compared. Okay, so now we can start talking about what actual things we've seen and learned during this whole journey of using Spark. We'll be using Spark for the last 3.5, 4 years in production. So this has been quite a few stories that we wanted to share. And before we kind of begin, I just want to point out that if you haven't noticed, our use cases of Spark is kind of different than most other talks you see. In most talks, you'll see people writing custom Spark jobs and kind of tuning their own plans so that the plans can run faster. But for us, it's really the customers building their plans, and we have to be able to generate our Spark queries based on customers' use cases, which means we don't have a direct control over what's being executed in Spark. And that, as we will soon see, actually leads to a lot of interesting cases. Okay, on to lesson 1, nested SQL. SQL, if you're familiar with it, it requires all of the computed columns to be nested. What does that mean? If you have a select statement and you try to define 2 fields, right? C1 is being defined as 1, and you want to do C2 as being C1 plus 1. This is actually a syntax error. SQL does not allow you to have 2 new definitions and have one definition require reference to another one. So then the way it works is you have to nest it. You have to first create C1, and then do an extra select clause to select C1 and do extra computation on it. So then we see this use case of customers having to build extra computed columns into their data sets. And what do? We need to abstract this away. But then we also need to be able to execute it on top of Spark. So how does that work then? So the first version we naturally thought of is have one nesting per computed column. And as you see, when you have many, many deep levels of nesting, it doesn't really scale to hundreds of computed columns. And because it takes a very long time to compile and optimize. because every time you add a new computed field, the catalyzed optimizer has to go through, traverse the tree, and be able to analyze and try to optimize those to the physical plan that it finally executes. So to give you an example, in this case, we have 3 base columns, first name, last name, and income. And we have 4 derived columns, full name, federal tax, state tax, and email. And if you do a topological sort of this, you see that there are 3 of them that are actually independent of them, and they can actually be computed independently. Whereas you have the last one, the email, that actually depends on the first name. Then this is the first plan that we used to generate. It'll be just nested SQLs all the way around. And this is obviously not a very good idea, because like I said, when you get to hundreds of levels of nesting, because customers will define hundreds of computed fields, this is not a very scalable way to go about it. So then the lesson here is we need to topological sort it and decide how to send this in different levels. And in this case, after the optimization, we're able to shorten this down to only 2 levels. So that's the first lesson. To another part of this is about actual plans being generated. So now, even though we are reducing the level of nesting, it doesn't mean it saves us from having plans being generally very big. Because plans, as they're built by people and customers that are using this sort of more high-level product, they tend to have many duplicate operators. And what do I mean? For example, let's say you have a use case. You have a bunch of transactions, and you want to be able to aggregate them to different levels, right? So you want to aggregate it by day, by month, by year, or go a little deeper by minute. So, and then you want to union them all together. So what do? You would first take this data set, do a group by on the day, and then you would take the same data set and group by the hour, and then you would union them together. So now the base data set is being referenced, the thing that is being grouped by on top of, this is being referenced twice, right? So we need to be able to identify these cases and not do the same computation twice. So to give you a more concrete example, in this case, we have a union. And the union has 3 different legs. There has a sample, a join, and a join as the immediate child operators. If you squint a little, you see that all these samples are actually the same data set, like the previous example I've given. So we need to be able to deduplicate this. So to deal with this problem, in our logical plans, we have come up with this new operator called cache operator that can identify these duplicate parts so that we can also tell Spark to not do the same computation multiple times. So in this case, we identified the sample as a duplicate, so we mark it as ID equals to 1. So then the next time we see it, we refer to the referenced created operator directly. If you see a little closer, you also see that the actual second join and third join are actually exactly the same. So we do the same thing here to, again, reduce the amount of duplicate work that we do. And so this is good now on the logical side. Now we bring it to Spark, and Spark is able to do the execution, and that's great. But one thing that we actually noticed is Spark, as a way to help you debug, would print the plan as a tree, right? And this is what they actually would print. In this case, we have a self-join, a data set that is joined to itself and then joined to itself again. And Spark, you'll notice that the tree strings that's being generated is not being deduplicated. So again, this will suffer the same problem about Blowup, because the same string, when they have many levels of duplication, plus with, let's say, the previous problem we had with nesting, this has an exponential growth. And when the use cases get more and more complex, the operators that's being generated becomes more and more ridiculous. So again, we need to identify these cases and be able to deduplicate them. So we have also modified the Spark operator in this case so that we can identify these similar or the same subtrees and replace them so that we can refer to them as line numbers instead to improve the performance in this case. On to the third lesson. My clicker is behaving weird. So now we're finally getting past the logical execution. Let's talk about the physical execution. the case I want to talk about here is broadcast join. For the people that have a little bit of database background, broadcast join is one specific way to execute a join. And the way it works is, as you see in the example, we have two nodes in a distributed fashion, and we have two tables that we want to perform the join on. Let's say we want to do the join on the second column, the numeric column. How does broadcast join work in this case? Well, as the name implies, we broadcast the table that is usually the smaller table into both of the nodes so that the same data, as we see in this case, the smaller data, exists in its entirety on the node. And when you have the entire data on the node, that means you can do all of the lookup and all of the execution without having to traverse through the network or have to communicate with another node, which means all the joins you do, the result can be simply concatenated together to get you the final result. And this is very efficient because if you have data that's broadcasted, then you don't have to incur the extra network cost of doing this computation. So this sounds like a very good thing, and ideally we want to do this all the time. So then what is the problem with it? Well, Spark's broadcast mechanism is actually quite inefficient. And the main reason is that the way it's being implemented, it's implemented on top of the broadcast variable primitive. And the way the broadcast variable works is the driver would first do a collect on the data that is being executed, and then so that the data lives into the driver. The driver will spill as necessary, but sometimes it doesn't work as well as we would expect. And then driver tries to use an efficient mechanism to distribute it to all of the executors. So the de facto way today is the torrent executor where the data gets chopped up into multiple pieces. So the executors, as they receive it, can also become a source of the chunk of data for other executors. But the fundamental part of this problem then still is the data has to go to the driver. And that is not a very good thing because when you have a lot of data going through, it's not very reliable. So then you might ask, if you just set the limit to be very low, that would solve the problem, right? Well, not quite, because in this case, there's no global limit on the broadcasted data. The data that's being broadcasted, let's say we make it by default, is 10 megabyte. It's 10 megabyte per join. If you only have one or two joins, that's great. But if you have joins like ours that have 100 joins, 200 joins, that's not very good because you end up shipping gigabytes of data into the driver, again, making the driver unstable. So what's the first reaction to this then? We should disable broadcast joins. So we first disabled it, and the expectation then is we have a small number of joins, but they're all rather large. So imagine we're joining the worker table to the transaction or their time off PTO table. The worker table is probably the smaller one, but it's still tens or hundreds of thousands of workers, and that's still hundreds of megabytes or a small number of gigabytes large because the table tends to be wide. But after we ran this for a while, and we actually realized that in many cases, customers actually do that on top of doing other joins that are rather small. So even in this case, customers are still doing joins like joining against the gender table, or in the previous example I gave you, they would try to join on, let's say you want to aggregate something in terms of number of months in a year. So you would join it to a month table, and the month might have some specific property. A month is only 12 rows, so the data is actually very, very small. But because we disable broadcast join, now all these data need to be shuffled around the network, and that makes the execution pretty slow. So the lesson here then is we again re-enabled it, but really re-enabled it for a smaller extent. So in this case, we re-enabled it so that it's only 1 megabyte. So that, let's say even if you have 100, it's 100 megabytes, it's not the end of the world. So this is a unique problem that someone like us who generated data from user input will likely face. And Pavel will take over from here.
Okay, so So we spoke about data prep a lot, and of course data prep is an intermediate result. It's not a final result. It's not something that people look. Use data prep to create the representation of the data, which is stored on the disk and easily queried in the good format by query engine. So several words about query engine, which of course is also powered by Apache Spark. And you can imagine, like, we use, in this case, a long-running process, a relatively bigger size Spark cluster as a memory database, which loads on demand the data blocks prepared by the prep, caches them, and serves the query. So in this picture, so like 1, 2, 3, 4, the query engine is number 4. That actually like powers all other user interfaces like this one, but also like reporting or executive dashboards and more. So one lesson we learned here is actually very simple. One use case is, for example, here, like we have the locations and billings, and we need to group by billing location. Summarize by location, relatively simple SQL, right? Select, sum, group by, billing location, no problem here. And the result is there. So the result looks really great, right? Great to data scientist, not to financial person. Because for financial person, the California is the same, doesn't matter how you write it. So, that's why in Workday, actually, we learned that all grouping on the string columns is case insensitive. Not a big problem, right? So just like use the upper function, choose one, sum, upper, and then you get the right answer. This is exactly what the customer wanted. Problem solved. And the problem is, turns out it's actually not that fast as it's used before. So we had the group by string. Now we do group by upper and min. Very small change. 7 times slower. 7 times. Okay, now we started to investigate. So what goes on here? First, in Spark, aggregation of strings uses a sort aggregate operator. And turns out it's not really fast as the other one, which used as a hash aggregate operator. But hash aggregate doesn't support strings. So we went into the code and modified Spark hash aggregate operator to support strings. And the first result, like moving from sort aggregate to the hash aggregate, we went from 7x to 3x, small change. Still a lot, need more. So we said like, okay, what goes on inside it? And then we learned that actually in Spark hash aggregate operator, the functions used there are evaluated twice. Okay, now it's a nice optimization. So we did the small change to make it evaluated just once. And now we are down to 2x regression. Still costly, so what we can do more? And more we say like, okay, like where we spend the time? Actually, we spend time inside the upper function itself. And then, okay, how we can solve it? So we can say like, okay, let's pre-compute the uppercase for all characters. And then use, instead of using the function, which goes and does the conversion on each char, we use the simple array lookup. And interesting enough, by using the optimized upper, instead of like the upper from the code, we reduce it to 1.5x, which is bearable, and we are still looking for some other like methods to actually take it down. So that's kind of one example how you actually can go and look below the hood and optimize Spark. So, and actually in this session, we wanted to speak about how we run multiple Apache Spark clusters in our environment. Prism has been more successful than we actually expected. We went from 0 to 100 customers, and by today actually to 200 customers in less than 18 months inside Workday. It's been probably the most successful product since the very first product of Workday. And it means like we run like many hundreds of Spark clusters across 3 production and 2 disaster recovery data centers. And how we do that? We use HDFS to have the data for all the customers, and of course it's encrypted. So each color represents different customer, right? Different tenant. But compute resources are pre-allocated and per tenant. So per tenant environment, it may be like production environment, sandbox environment, impl environment, disaster recovery environment, so several environments per customer. So, and that it means like we run a moderately sized Spark cluster for each tenant. It always runs there because we run queries, right? 70% is queries, another 10% data prep interactive, and the rest is pulled for data prep batch applications. So that actually like works very well, and it's easy to provision, it's easy to monitor, it's easy to increase or decrease, and it's resource isolation, so they don't influence each other, but it's not very optimal. And each time you want to change the version, you lead to downtime, essentially. So no load sharing, and there are some techniques how to do that, and we've started to work on that, but then we understood the feature is not there. The feature is actually multi-tenanted Spark clusters. And that's what currently we've been working on, meaning that we make our Prism server to be stateless, so it can serve multiple customer tenants, and then Spark cluster will be bigger, but also multi-tenanted, serving multiple tenants as well. So you see like each Spark cluster now has like multiple colored blocks. And in some cases, we use Spark built-in functionality. In some cases, we build on top of Spark functionality, like for fairness. So we don't want some very active tenant to cannibalize and take resources from other tasks. We want to have like effective load sharing. Some cases we need to actually add functionality missing in Spark. For example, here we use encrypted data on HDFS. So we need to have the per job Kerberos impersonation for long-running jobs to solve this problem. So it's pretty interesting journey, and we're about like 40% into it. It will take like probably another year to get there. And it already sounds like a great topic for the next year presentation. So if you happen to be around like next year for Spark Summit, that's one option. But frankly, you don't have to wait the whole year. You can come and build the future with us together at Workday. So if you got you excited about what we do and how we learn and how we make fun, speak to me, speak to my colleagues. We have a small booth at the exhibition floor. And we have several minutes for the questions.
Thank you.
Thank you.
Yeah, for those who have questions, you know, it's helpful if you line up. You can ask a question here. If there's a couple here, I can hand the mic around.
Hello. My question is related to customer data. So is the customer data, have a same format or is in a different format? And second, how customer are giving the step, whatever the operation they want to apply on that data? Question clear or not?
Did you say it's the same volume or same?
I'm asking what format your customer
What format?
Yes.
It differs a lot. So usually we try to when we get the data from other systems, we have several ways to bring the data in. So the simple way is actually to say like convert everything into CSV and bring it over using SFTP. We also have APIs, and more people use APIs. We have partners which actually like you can use like third-party ETL to connect to your data and bring it over to Prism. So very much depends on different customers. Yeah.
This is CSV and this is a column they want to analyze. So they have something CSV with metadata or something different?
So usually that's where data prep shines. You can bring the CSV file, and then you can like assign like the type of the data, what it does, and then you can like create computed columns, or you do some parsing. For example, split the string into several fields, so that everything is done in data prep. So that allows people actually to bring the data in a kind of like semi-structured form, and then make it structured inside Prism. So inside Prism, once you publish it, it's already very well-structured form, and we know the schema, and that allows us to run queries really fast.
So how you're deciding when you are processing that CSV, how you're deciding number of partition on Spark? Because if you go on Spark CSV, right, so it's maybe have single partition for large CSV.
Yeah, it's based on the Hadoop partitioning. So by default, let's say a Hadoop block is 128 megabytes. So it'll be one partition for that big.
CSV is only a single block, then that means it's a single task?
It could be, yeah. Then if it's only one block, then it wouldn't take any very long either way. So.
Okay, thank you.
First, thank you so much for sharing about it. I think it's a great presentation. So I have an additional question on the publishing side of data prep. I'm just curious, like, does it allow users to schedule the data pipeline?
Yes.
Then my next follow-up question is that how did you implement the data orchestration part of scheduling Spark jobs?
So in this case, we actually leverage the Workday schedule mechanism, part of the platform. So they've been doing that. Usually, it depends on the customer requirements. When you need the data each time, like usually we suggest to do it like to schedule during the night. So it will crunch the data, and then you come in the morning and you have the fresh data. In some cases, like more analytical use cases, people say like I only need it like by the end of the quarter or by the end of the month. So I will just wait until then. We also allow people to actually to kick off the publishing process manually. So if like your CEO wants the data now, you click the process, you go get the coffee. Usually like we can do it like in 10, 15, 20 minutes. But some very big use cases, especially like history going back 2 years, usually take like might take like several hours.
Thank you.
Thank you so much for the talk. I guess a question I have is about the way in which you guys optimize things in terms of the piece where you have like nested join or SQL joins, or columns actually. What are some of the pros and cons of taking a series of with clauses and then having just a long series of joins at the end of that of just very narrow tables onto the original large table?
Have a series of, sorry?
With clauses.
With clauses. So the thing with clauses is it's a nice alias type of construct, but when it's executed, Spark actually will embed this into, well, basically substitute the expression with the places you reference it. So it still gets executed multiple times. So that's one part we also could make better, but it doesn't right now.
Okay, thank you.
Hi, I'm kind of curious about, you said you had like your prep staging of preparing the data with Spark, and you had your interactive preparation of data as well, and then you ended
Could
up
you speak
using...
a little louder, sorry?
So you ended up using Spark as a query engine, and I was wondering, like, after the data has been computed in the pipeline in Spark, in like the, I forget what it's called, like the second section and the interactive section, why did you end up choosing Spark as your query engine? And like, did you consider something like, so for example, like for also integrating transactional data from other data sources? And also, how did you deal with transactional in general? Like, was it everything exported in HDFS daily, or did you need something that was more up to date?
So yes, we could use like Presto or even like Spark SQL to actually to query the data after data preparation. But first, it will not be as fast because we actually run long-running the Spark job, and we cache the data. Also, we do some on top of the Spark in query. We also do like multiple optimizations, which we don't have time to cover here, but we try to do it like faster. In addition, we serve the company which has like companies which have like tens or hundreds of thousands of employees, meaning like hundreds or thousands of executives which run the query at the same time, and everybody wants it fast. So if you do like 1,000 Presto jobs and then multiply by number of customers we have, it doesn't really scale at the same time, right? So we kind of like, it's a different world. We don't serve like 5 data scientists, right? We serve like 1,000 of HR and financial execs. Make sense?
How about now? Yeah, great. So quick two-part question on Prism. First part is, how restrictive is Prism to use cases? Is it ATM type use cases and types of data? The second part is, if it is indeed restrictive rather than solving all global analytics, then why don't you enforce certain ontologies and save all the self-serve work for users to prepare data, your APIs can probably transform in an automated way.
Okay, very, very good question. So Prism is generic analytic tool, so we cover like 20 plus different products in Workday portfolio, like human resources, benefits, learning, recruiting, expenses like financial, suppliers, and all of that. So when the data comes from Workday, because we have the object-oriented server, we know the ontology, we know the schema. So when we bring the data from Workday, you don't need actually to go and remap it. It comes there. But when the data comes from external system, where we don't know the schema, and actually there, like actually data prep is much kind of like more available.
All right, I know we're definitely out of time. So I know there's a few more questions. So Pavel and Jianneng, if you can meet a couple people in the back, you can follow up a little bit more. But once again, thank you, Pavel and Jianneng.